I, Jahan Patel from the Institute of Engineering and Technology in the Department of Electronics and Communication. Welcomes you to the session of electromagnetic theory. Today we are going to discuss about Unit 5, that is plane wave and boundaries, and discussing media with the topic perfect dielectric and boundary condition. In the previous session we have discussed about the boundary condition for the electric field. Now in this session we will see about the magnetic field boundary condition. So based on the electric field boundary condition, let's see one example related to it. So the problem statement is given E1 bar, electric field is given, that is 2kx minus 3ay plus 5 inside volt per meter at the charge distribution. You have to find D2 bar. D2 bar is the flux density at medium 2. You have to assume that epsilon R1 relative permittivity is 2 and epsilon R2 is 5. Here, consider this figure. Here in this first medium, electric field is E1 and in the second medium, electric field intensity is E2. Here, for this, the boundary is of z-axis. Here, whenever whatever boundary is given, you have to take that direction component as a normal component. So here, if you see the figure, here z direction is given as a boundary. So you have to take that direction component as a normal component. So here, from the E1, you have to take z direction component as normal component. That means En1 is nothing but 5z. Okay. So total E1 is addition of normal component and tangential component. So normal component is given, that is 5z. So 5z and tangential component, that is 2ax minus 3ay, because you have to subtract E1 minus En1. So tangential component is 2ax minus 3ay. From the boundary condition, Et1 is equal to Et2, means two tangential components are equal according to electric field boundary condition. That means 2ax minus 3ay is equal to Et1 equal to Et2. Now, if you have the value of Et2, you can easily find out Et2, because ultimately we have to find the D2 bar, and D2 bar is addition of tangential component and normal component. So basically we require dt2 and dn2. So let's first find out dt2. So dt2 is equal to epsilon 2 into et2. Okay. So first let's put the value of et2 in this equation. For this you require epsilon 2. Epsilon 2 is epsilon 0 into epsilon r2. Okay, multiplication of free space permittivity into relative permittivity. So epsilon 2 is the epsilon 0 into epsilon r2, means 5 epsilon 0. Okay. So dt2 is that epsilon 2 into the particular value of the et2, that is 2ax minus 3ay. So finally the dt2 value is 10 epsilon 0 ax minus 15 epsilon 0 ay coulomb per meter square. This is our value for dt2. Now let's find out the normal component. So according to the normal component boundary condition, dn1 minus dn2 equal to rho s. Okay. So dn1 minus dn2 is equal to rho s, but in case of the perfect condition or ideal condition, rho s should be 0. Now if rho s is 0, so dn1 minus dn2 equal to 0, then dn1 equal to dn2. Now this dn1 is nothing but epsilon 1 into en1. Okay. Epsilon 1 is the multiplication of epsilon r1 and epsilon 0. This relative permittivity into free space permittivity into en1. En1 is 5az. Okay. So final value for dn1 equal to dn2 is 10 epsilon 0 az bar coulomb per meter square. Now let's find out d2, because d2 is addition of normal component and tangential component. So you have to add both the component. So if you put both the values of dn2 and d2, you get the final answer, like 10 epsilon 0 ax minus 15 epsilon 0 ay plus 10 epsilon 0 az coulomb per meter square. Here in this equation, if you put the value of epsilon 0, that is 8.85 to 10 raised to minus 12, then you get the final answer like this. This is the final answer for d2 bar. Okay. Now let's see magnetic field boundary condition. So for magnetic field boundary condition, again we have to take the case of the tangential component as well as normal component as we have done for the electric one. So let's do it for the normal component. So if you see in this figure, for the normal component, the one box is there, and for the box on the top side and at the bottom side, you can see this top side in which En1 component is applied, and at the bottom side En2 component is applied. In between medium 1 and medium 2, now this is magnetic field. So obviously two mediums have different permeability of μr1 and μr2. Okay, and it is separated by one sheet charge that it has some density. So here you have to apply the Gauss law. But Gauss law for which field? Gauss law for magnetic field. So that's why let's apply the Gauss law for magnetic field. According to the statement, total surface integration of magnetic flux density is equal to 0. That means surface integration of V dot ds is equal to 0. Now this V dot ds is addition of all the 6 sides of cube. That means it should be the addition of front side and back side, left and right side, top and bottom side. So in short, all the 6 sides should be added for this integration term. So it will be like this. Surface integration BDS is integration for the top side BDS, bottom side BDS, left side BDS, right side BDS, front and back side BDS. But if you know that the components are applied only on the top and bottom side, so obviously the other 4 terms of the integration will become 0. So the total integration of BDS is the addition of only 4 terms that are the top side and bottom side. That means surface integration of d dot ds becomes the total top side integration and bottom side integration. The other 4 integration terms will become 0 like this. Okay. Now the final equation for the total BDS is addition of top and bottom. Now if you remember, the top side will denote the positive z-axis and bottom side will denote the negative z-axis. So obviously for the top side BDS, the component that we applied from on the figure is Bn1. So the direction is positive z, and that's why your direction is plus az bar. Obviously, if z-axis is constant, then which axis are valid? Dx and dy will vary into az. Obviously, z dot az is 1, so that's why Bn1 into delta x delta y, because x and y range is from 0 to delta x and 0 to delta y. So that's why the final answer for this one is like this. And for the bottom side, the same case will be considered, but obviously the direction for the bottom side is negative z, and if the direction is negative z, you have to put here over here minus az. So az dot minus az will become minus 1. Okay. So this is minus Bn2 delta x delta y. This is the final equation for BDS. Bn1 delta x delta y minus Bn2 delta x delta y. So Bn1 minus Bn2 delta x delta y is the equation for surface integration B dot ds. Now this surface integration B dot ds should be equal to 0 according to the Gauss law for the magnetic field. Now, if the total integration of B dot ds will become 0, that means our equation Bn1 minus Bn2 into delta x into delta y will also become 0. That means we can compare both of these normal components with each other. That means Bn1 will become equal to Bn2. Okay, like this. Bn1 minus Bn2 into delta x delta y is equal to 0. So ultimately it will become Bn1 equal to Bn2. So this is the normal component boundary condition for magnetic field. Now let's move towards the tangential component. So as we have done the tangential component derivation for the electric field, that is in which we were considered one rectangular path and we have done some integration. So the same thing we have to apply it over here. But for this, please remember that for this case, we will apply the Ampere circular law. So let's start. Here, please see this figure. Here, the rectangular path is ABCD and it has the component of magnetic field intensity, that is HT1 and HT2. You can see this is HT1 and this is HT2. So here, if you see this figure, you can note that the components are present only on horizontal line, not on the vertical line. And that's why when we take the integration and make an addition of all the four sides, then we have to neglect the vertical side of the rectangular part like this. Here, obviously, total integration is addition of all the four parts A to B, B to C, C to D, and D to A, HDL. But we will make the vertical path as 0. Why 0? Because we have applied the tangential component at only horizontal axis, not on the vertical axis. And that's why B2C and B2A will become 0. Only the two things that are remaining is like this. A to B H dot DL and C to B H dot DL. Okay. For A to B H dot DL, integration will vary from 0 to delta x. Component that is present over this path is HT1. Axis that is changing the difference. A to B H dot DL is 0 to delta x. HT1 AX into DX AX. So AX dot DX will become 1. So HT1 into delta x is our H dot DL. For B2C, it will be delta x to 0 because obviously the direction is opposite, so we have to do the integration from delta x to 0 and it will be like this minus ht2 into delta x. Now we have to make the addition of all the four terms, but we have only two terms because vertical will become 0. So the final equation is ht1 delta x minus ht2 delta x. Delta x will be common, so it will become ht1 minus ht2 into delta x. Now this integration of HDL is nothing but the total current type, and current itself has its component like current density into that particular path, means KDL. So here DL will be considered as a delta x, so it will be K delta x. So if we compare both these equations, then HT1 minus HT2 into delta x will become K delta x. Delta x and delta x will be cancelled out, and final equation is HT1 minus HT2 equal to K. Okay, so this is the equation for the vector form that we have to multiply with the direction, that is E and cross A. Okay, so that is about the magnetic field boundary condition. Okay, now up to this, if you have any doubt or queries regarding the session, you can ask me. I am available. Thank you for watching.